Welcome to your next chapter. So in this section, we're going to be talking about atomic theory. So atomic theory really deals with how atoms are structured, how they're kind of composed and built, and then also deals with a lot of the experiments that led to these discoveries and our understanding of the atom itself. So first up, couple laws that we have to talk about. So you have the law of conservation of mass. So this states that mass is neither created nor destroyed during chemical reactions or physical changes. It can be changed, it can be converted, but it cannot be destroyed or created. You also have what's known as the law of definite proportions. So in this, says that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So if you have caffeine that comes from, say, a tea leaf versus caffeine that comes from a coffee bean, they are going to have the exact same chemical composition, okay? So you're going to have the exact same number of carbons, exact same number of nitrogens, oxygens, hydrogens, and phosphorus, I think is, I think there's a phosphorus in there. And they're all going to be bound together in the exact same way. Okay, that doesn't matter if the caffeine is grown in a plant or if it's synthesized in a lab. And then for a slightly easier example, methane gas, if you have methane, it's always going to be CH4. So 1 carbon to 4 hydrogens, okay, no matter where it comes from. You also have the law of multiple proportions. So this is where it gets a little bit weird. So if 2 or more different compounds are composed of the same elements, then the ratio of the number of each element will be different by at least 1 number. Really easy example with this is you've got water and hydrogen peroxide. Both are made up of hydrogens and oxygens, but where water has 2 hydrogens and 1 oxygen, hydrogen peroxide has 2 hydrogens, 2 oxygens. So they have the same elements, but the subscripts are going to be different, okay? And that is enough to make them completely different compounds, right? There's a chemistry joke, sorry, but I love this one. It's, guy walks into a bar and orders an H2O, and his buddy orders an H2O2, and then he dies. So it was an elaborate assassination attempt. Anyway, alright, so this is kind of a different way of looking at this. So the law of conservation of mass. So we have our 2 hydrogens on the left here, and you can see their total mass, just with the 2 hydrogens there. You also have your oxygen atom, and you can see the total mass there. And then when you combine them, you actually have the mass of those 3 atoms total. Okay, so added together. And then again, in this instance here, we have a phosphorus pentachloride molecule breaking up. And so you're going to have 2 of the chlorine molecules bond together. And then you're going to have the remaining 3 chlorines and the phosphorus bind together. Okay, so if you look, the sum of the phosphorus trichloride molecule and the chlorine molecule, their masses equals the sum, or equals the mass of the phosphorus pentachloride. And then one final example here, we have sulfur and oxygen combining to form sulfur dioxide. So the sulfur, you add in the mass of the 2 oxygen atoms, and you get the mass of the sulfur dioxide molecule. So the law of multiple proportions. Okay, so basically, anytime you have nitrogen monoxide, you know it's going to be 1 nitrogen, 1 oxygen. Okay, if you have nitrogen dioxide, it's going to be 1 nitrogen, 2 oxygens. Okay, so each of those individually is the law of definite proportions. But when you look at the 2 of them, because they have the same 2 elements, but they're just in different proportions to each other, that is the law of multiple proportions. Okay? All right, so getting into atomic theory. So the idea of the atom really started with Democritus. He was a Greek philosopher. This is what they think he looked like. He proposed that matter consists of invisible particles called atoms. So he was the first one to actually name the atom. And again, with him, it was all just thinking about it. He wasn't actually able to do any kind of experiments to prove the existence of an atom. Okay, so this is his model of an atom. Basically, it looks like just a ball, okay, a ball of matter. So he developed this theory by observing someone splitting a stone in half. So his idea was, if you continue splitting it in half, eventually you're going to get to something that can't be split in half. And that's what he called an atom. Here we go. So he believed that atoms were indestructible and unchangeable. So you couldn't split an atom, which we know is not true, and you also couldn't change anything about an atom, which we also know is not true. So while he did kind of have the right idea going into this, he was wrong on several key points. So he also believes that atoms are solid. As you will see in a little bit, they are most certainly not solid. Alright, fast forward several centuries, and now we get John Dalton. So Dalton was an English chemist and a teacher. This is what he looked like. He proposed that all matter is composed of extremely small particles. So at this point, he's still kind of right in line with Democritus. He also called these atoms. Okay, so his model is almost identical to Democritus's model, except he started adding in some more details. So atoms of a given element are identical in size, mass, and other properties. It's technically correct in some ways and incorrect in others, but we'll get into that as we go along. So atoms of different elements differ in size, mass, and other properties. Okay, so that is relatively correct. Atoms cannot be subdivided, created, or destroyed. Okay, so created or destroyed, yeah, that's good. Subdivided, though, we know that there are such things as subatomic particles. So you can't actually split an atom into those subatomic particles. And then he was the first one to actually propose that different atoms can combine to form different compounds. Okay, so he was the first one to actually think about chemical compounds versus just atoms. Because before him, especially back in Democritus's time, they believed that, stone was an element. Okay, they believed that wood was an element, not that wood was made up of several dozen different elements, okay, all coming together to form different compounds. So Dalton was the first one to really talk about the compounds themselves. Now we go on to J.J. Thomson, again, an English scientist. So he came up with what's known as the plum pudding model. That is a very British name for this model. Most Americans know it as the chocolate chip model. Okay, so in this model, you have a positively charged sphere, okay, which would either be the cookie part of it, or in Thomson's model, it would be the pudding part of it. And then you have the electrons just kind of studded on that positively charged sphere. So those would be the chocolate chips, okay, or the plums. So each atom is a positively charged sphere, and then it has the negatively charged electrons scattered across the sphere. So what you might notice here is that this is the first model that brings up negative and positive charges. Okay, he did his experiments with what's known as a cathode ray tube. I'm going to try to find a video for you about what this looks like. Okay, well, maybe I actually have one. So, cathode ray tube is basically just a glass tube, and it's filled with gas, I believe it is, and then they shoot a laser through it. And there are also two charged plates that they have in this. Okay, so you can see the negatively charged plate up on top here and the positively charged plate on the bottom. So you shoot the laser, which is basically a stream of electrons, through this cathode ray tube. Actually, I think it's a vacuum on the inside. Yeah, it would be a vacuum on the inside. It's not, it doesn't have any gas in it. So it's basically moving through empty space. So the only thing that is affecting the beam of this path is the charge on these two plates. And so you'll notice that the beam bends towards the positive end. So here we go. Passes an electric current through a vacuum tube, produces a glowing stream, and Thomson discovered that the stream would bend towards the positive charge plate. And so even at this time they knew that you had two different charges, positive and negative, and they would attract each other. So it can't be a positive charge that's bending towards the positive charge. It has to be a negative charge. So he theorized that the stream was made up of small particles, which were pieces of an atom with a negative charge. And he was right about that. So this was the first evidence of an electron. And he was also able to measure the charge to mass ratio. Not hugely important in this class, but it becomes kind of amazing that he was able to do that later on in further science. And there's the video. So I'll post that in the notes. Alright, next up we move to Millikan and Harvey Fletcher. So they were American physicists, and I believe it was, oh, give me 1 second. So this is another example in science of one person doing a lot of work, then actually making the discovery, and then through a set of random circumstances, somebody else gets to take credit for it. And in this case, Robert Millikan was a research professor, and so Harvey Fletcher was actually one of his grad students. Now, Harvey Fletcher was the one who did all of this work, but because he was in Millikan's lab, Millikan was the one who was able to publish as the first author and got the credit for this discovery. But Fletcher was able to measure the electrical charge of an electron. Okay, and he did this what's known as the oil drop experiment. So with this, you actually would spray oil into this contraption, and it would spread out in this very fine mist. And then you would have a pinhole inside of a positively charged plate. Okay? Then you also had a negatively charged plate on the opposite end. So, once you drop some of these oil droplets in between these two plates, you would hit them with an X-ray that produces a charge on the oil droplet. It's a negative charge. And then by manipulating how large the charges were in the positive and negative plates, they were actually able to suspend the oil droplet between the two plates. And by balancing it, he was able to calculate the exact charge. Okay, there's a lot of math that goes into all of this that we will not be dealing with because it gets really complex, and yeah. So it's, again, a huge deal that he was able to discover this, that he was actually able to measure this incredibly precisely, and then his research advisor took the credit for it. So, alright, that's where we're going to stop for this first video, and we'll pick up with the next scientist in just a sec.